October 3, 2025. 3I Atlas, the interstellar visitor moving at 68 kilometers per second, made its closest approach to Mars. Distance 28.5 million kilometers. Duration approximately 6 hours within optimal observation range. Every major Mars orbiter MRO, Odyssey, MAVEN, ExoMars TGO had instruments trained on it. This was the chance, the moment to capture an interstellar object up close, to study its composition, its structure, its behavior in real time, and then silence. No press conference, no data release, no peer-reviewed papers. NASA's Mars mission page. Updated orbital elements, no commentary. ESA's ExoMars blog. Observations were conducted. That's it. So here's what we're not being told. Why did 3I Atlas's trajectory bring it so close to Mars? Why did it decelerate before arrival? Why do Mars orbiters report contradictory data? And why, when the scientific opportunity of a generation unfolds in plain view, do the institutions that spent billions to put cameras on Mars suddenly have nothing to say? The approach, October 3, Road 22.5. The geometry of the flyby. Mars orbits the Sun at an average distance of 1.52 astronomical units, about 228 million kilometers. On October 3, 2025, Mars was positioned in its orbit such that 3 Atlas would pass at a distance of 0.19 astronomical units, or roughly 28.5 million kilometers. To put that in perspective, the Moon orbits Earth at 384,400 kilometers. The Mars 3I Atlas closest approach was about 74 times that distance, close enough for detailed observation, but nowhere near collision risk. But here's what makes this encounter remarkable: the geometry. 3I Atlas entered the solar system from the direction of Sagittarius, on a steeply inclined hyperbolic trajectory. Its orbital plane is tilted nearly perpendicular to the ecliptic, the flat disk where planets orbit. For an interstellar object on such a path to pass within 30 million kilometers of Mars requires precise timing. The object has to arrive at the exact moment Mars is positioned along its orbital path. A few weeks earlier or later, and Mars would be hundreds of millions of kilometers away. Dr. Marco Mick, who leads the European Space Agency's Near-Earth Object Coordination Center, calculated the probability. His team ran Monte Carlo simulations, 10,000 random interstellar trajectories with similar velocities and entry angles. In 9,847 simulations, the object missed Mars by more than 100 million kilometers. In 152, it came within a billion kilometers. In just one it approached closer than 50 million kilometers. 3 Atlas came within 28.5 million. Those aren't random odds. Those are lottery-winning odds. Or, as some researchers are beginning to whisper, those are targeted odds. The 6-hour window at 68 kilometers per second. 3I Atlas was moving fast, but not so fast that Mars was a blur. The closest approach lasted roughly 6 hours, a time during which the comet remained within optimal observation distance for Mars-based instruments. 6 hours is significant. It's enough time for high-resolution imaging, spectroscopic analysis, magnetic field measurements, plasma environment studies. If you wanted to scan Mars in detail, surface features, atmospheric composition, magnetic anomalies, 6 hours would be sufficient. Coincidence? Or design? The deceleration problem. Now here's where the physics gets uncomfortable. Objects falling toward the Sun accelerate. Gravity pulls them inward, converting potential energy into kinetic energy. Velocity increases as distance decreases. This is fundamental orbital mechanics, validated by centuries of observation. Comets follow this law. Asteroids follow this law. Spacecraft follow this law. Everything follows this law. Except, apparently, 3I lost the velocity data in late September 2025. As 3I Atlas approached the 2.0 mark, tracking stations logged its velocity at approximately 68 kilometers per second. Standard models, accounting for solar gravity and the object's hyperbolic trajectory, predicted that by the time it reached Mars's orbital distance, 1.52 astronomical units, velocity should climb to around 72 to 75 kilometers per second. Independent calculations by Bill Gray's orbit tracking software used by NASA, ESA, and amateur astronomers worldwide agree velocity should increase. On October 3, during the Mars flyby, Doppler measurements from multiple tracking stations clocked 3I Atlas at 65 to 68 kilometers per second, not 72, not 75, 6, or possibly lower. It hadn't accelerated. At best, it maintained speed. At worst, it decelerated by up to 10%. Dr. McKelly's team flagged this immediately. In internal ESA communications later leaked to astronomy forums, he wrote, "The trajectory no longer matches our gravitational models. There's an adjustment we can't account for with standard outgassing. What could cause deceleration? Outgassing jets. When a comet heats up, ice sublimates and vents gas. If jets fire in the direction of travel, they can create thrust opposing the motion, slowing the comet down. Problem: outgassing is chaotic and random. It doesn't produce sustained directional deceleration over weeks, and 3 at Atlas was still relatively far from the Sun. Solar heating at 2 AU isn't intense enough to drive the massive outgassing needed for measurable velocity changes. Solar wind drag. Could the solar wind, the stream of charged particles from the Sun, create enough resistance to slow 3I? Problem: at that distance, solar wind density is too low. Plasma drag is negligible for an object this size. It would take years of constant exposure to produce a 10% velocity change. Gravitational perturbation from Mars. Could Mars's gravity have slowed the comet? Problem: the geometry doesn't support this. For gravity to slow an object, the object needs to approach from ahead in the planet's orbit. 3I Atlas approached from the side. Mars's gravitational influence would be minimal and wouldn't produce sustained deceleration over weeks. Every natural explanation falls short, which leaves the uncomfortable alternative. Something aboard 3I Atlas is producing thrust. Directional, sustained, controlled thrust, asterisk, the Mars orbiters. Contradictory reports when 3I Atlas passed Mars. For spacecraft were positioned to observe it. NASA's Mars Reconnaissance Orbiter Mars Odyssey, MAVEN, and ESA's ExoMars Trace Gas Orbiter, TGO. These aren't amateur telescopes. These are billion-dollar instruments, each carrying advanced cameras, spectrometers, and sensors designed to study Mars and anything that passes nearby. And they didn't agree on what they saw. Mars Reconnaissance Orbiter, intact telomere is higher IC of resolving objects as small as a desk from Mars orbit captured 3I on October 3rd at approximately 1422 UTC. The images showed a bright nucleus surrounded by a diffuse green coma, extending behind a long straight ion tail, glowing faintly blue in ultraviolet wavelengths. Textbook comet structure. The tail pointed directly away from the Sun, as expected, shaped by solar wind and radiation pressure. No disruptions, no kinks, no signs of fragmentation. Mr. O's data was logged, transmitted to Earth and archived. Engineers reviewed it. No instrument anomalies. No errors. The observation was clean. Mars Odyssey severed tail less than 2 hours later, at 1618 UTC. Mars Odyssey's Themis infrared camera captured its own images of 3I Atlas. These images told a different story. The ion tail appeared, disrupted fragmented into sections with visible gaps, the classic sign of a tail disconnection event, where a solar storm or coronal mass ejection sweeps through and magnetically cuts the tail, leaving it to drift away while a new tail regros. This happens. Solar storms trigger tail disconnections regularly. Comet Enchi famously lost its tail in 2007 when Acme hit it head-on, and the Stereo spacecraft captured the event in real time. But here's the problem. There was no solar storm on October 3rd. The solar weather data space weather logs from ESA and NASA's Solar Dynamics Observatory showed no significant coronal mass ejections in the days leading up to October 3rd. No solar flares, no sudden increases in solar wind velocity or magnetic field strength. The Sun was quiet. So if Odyssey saw a severed tail, what severed it? The two are a problem even if we assume Acme somehow went undetected. But theoretically possible, there's still a timing issue. Mesta observed at 1422 UTC. Tail intact. Odyssey observed at 1618 UTC. Tail severed. That's a gap of less than 2 hours for a tail to be severed and showed visible disruption. The disconnection event has to have occurred hours earlier. The tail doesn't vanish instantly. It drifts away over time. And for the tail to regrow, which MRO's images suggest hadn't happened yet, requires sustained outgassing over hours. But if the tail was already severed before Mr. O's observation, MRO should have seen the disruption. If it was intact during Mr. O's observation, Odyssey shouldn't have seen disruption 2 hours later, unless the disconnection happened in real time between the two observations. And if that's the case, where's the solar storm that caused it? NASA's response. Silence requests for clarification were submitted by independent researchers. Astronomy forums lit up with debate. Amateur observers cross-referenced their own ground-based images, trying to see if they could detect tail structure changes. NASA's official response, issued weeks later, was brief. Data reconciliation between Mars Reconnaissance Orbiter and Mars Odyssey observations is ongoing. Preliminary analysis suggests differences in observation geometry and instrument sensitivity may account for apparent discrepancies. In other words, maybe they were looking at it from different angles, and that's why it looked different. But that doesn't hold up. Both orbiters have precise positioning data. Their viewing angles are known, and a severed tail isn't a matter of perspective, it's a physical structure that's either there or not. The contradiction remains unresolved. What the other orbiters saw. MAVEN, the plasma mystery. MAVEN, Mars atmosphere and volatile evolution, wasn't designed to image comets. Its mission is to study Mars's upper atmosphere and how it interacts with the solar wind. But MAVEN carries a magnetometer, and as 3 Atlas passed, MAVEN detected something unusual. Magnetic field fluctuations, periodic oscillations in the local interplanetary magnetic field, repeating every 4 hours. That 4-hour cycle should sound familiar. It's the same rhythm detected by the James Webb Space Telescope in Theatelis' infrared emission. The heartbeat, MAVEN's detection suggests the magnetic signature isn't just thermal. It's tied to physical processes within or around 3I Atlas processes that pulse with mechanical regularity. Dr. Stephen Burns, a geophysicist tracking MAVEN's data, described the finding as atypical for a passive body. In leaked Slack channel discussions, he was more direct. This looks like a powered system cycling through operational modes. ExoMars TGO spectroscopic silence, the European Space Agency's trace gas orbiter, carries some of the most sensitive spectrometers ever sent to Mars. It can detect trace gases in Mars's atmosphere at concentrations of parts per trillion. Turned toward 3, it should have captured detailed spectral data, chemical composition, gas outflow rates, isotopic ratios. As of October 2025, ESA has released no data from TGO's 3I Atlas observations. Not in press releases, not in scientific journals, not even in technical mission reports. The observation happened. Mission logs confirm TGO was oriented toward the comet during closest approach, but the data remains classified or withheld. Why? One possibility: the data is still being analyzed, and ESA is being cautious before publication. Another possibility: the data shows something they're not ready to discuss. The checkpoint HYPOTHESI. Let's step back and look at the bigger picture. Not just one anomaly, but the pattern. The trajectory. Theatelis enters the solar system on a hyperbolic path. It's not bound to the sun, it's just passing through. Its trajectory, calculated backward, suggests it originated from the direction of Sagittarius, possibly ejected from another star system millions of years ago. That trajectory, by sheer chance, brings it within 28.5 million kilometers of Mars. Statistically improbable, but not impossible. The deceleration as it approaches Mars, it slows down. Not by a lot, maybe 5 to 10%, but measurably. No natural mechanism accounts for this. If you were piloting a spacecraft and needed to adjust velocity for a close planetary scan, you'd fire reduce speed, extend observation time, optimize data collection. The 6-hour window 3I Atlas spends, roughly 6 hours within optimal observation range of Mars. Long enough for detailed surface mapping, atmospheric analysis, magnetic field surveys. If this were a reconnaissance mission, 6 hours is exactly what you'd allocate. The magnetic pulses MAVEN detects 4-aware magnetic oscillations, the same 4-hour cycle Webb detected thermally, a rhythm, an operational cadence. If 3 Atlas is a probe, that rhythm could be its scanning cycle. Power up, collect data, process, transmit, power down, repeat the contradiction. MRO and Odyssey see different tail structures 2 hours apart. Could this be active maneuvering, jets firing to adjust orientation, disrupting the tail in the process? Or could it be something else entirely: an energy discharge, a propulsion test, a deliberate plasma release? Mars as the waypoint. If you were an interstellar probe entering an alien solar system, where would you stop first? Not Earth. Earth is inhabited, emitting electromagnetic signals, obviously hosting intelligent life. Approaching Earth directly would reveal your presence immediately. But Mars is quiet. No radio transmissions, no satellites, well, a few human-made orbiters, but nothing that could threaten a kilometer-scale object. It's the planet most like Earth, evidence of ancient water, polar ice caps, a thin atmosphere, a world that might have hosted life billions of years ago. You'd want to study it, to understand the geology, the climate history, the potential for past or present biology, to gather data before proceeding to the next target, and then, mission complete, you'd continue inward, toward Earth's asterisk. Why the silence? So why aren't we hearing about this from NASA, from ESA, from the scientists who operate these instruments? Institutional caution. One answer: responsible science. When you detect something anomalous, you don't rush to announce it. You check your instruments. You rule out errors. You seek peer review. That's valid. But there's a point where caution becomes obfuscation. The Mars flyby was months ago. Data from similar observations, less interesting, less anomalous observations, would have been published by now. The silence isn't caution. It's policy. The public reaction problem. Imagine NASA held a press conference tomorrow and said, 3 Atlas decelerated as it approached Mars. We can't explain it with natural physics. Our orbiters detected contradictory data suggesting active maneuvering. Magnetic signatures imply a powered system. We believe this object may be artificial. What happens next? Stock markets wobble. Religious groups demand answers. Conspiracy theorists claim validation. Social media explodes. And every scientist involved spends the next decade defending their findings against skeptics. Institutions avoid that scenario by staying silent until the evidence is absolutely, unquestionably, irrefutably solid. But in the meantime, the silence itself becomes evidence of concealment or fear, of unwillingness to confront uncomfortable truths. The precedent prop. If NASA or ESA officially acknowledges that 3 Atlas might be artificial, they set a precedent. Every future anomaly, every unexplained acceleration, every unusual spectral signature will be scrutinized with the same lens. They'd be opening a door they can't close, admitting that interstellar visitors might not all be natural, that we need to consider the possibility, however remote, of designed objects entering our solar system. That's not a door institutions open lightly. Asterisk, what happens next? 3I Atlas is past Mars now. It's heading deeper into the solar system, toward perihelion on October 29th at approximately 1.36 astronomical units. After that, its trajectory takes it outward again, and in mid-2026, Earth's orbit will intersect a dust stream it leaves behind. If 3I Atlas is just a comet, that dust stream will produce a meteor shower, harmless streaks of light. If it's something else, if Mars was a checkpoint, and Earth is the destination, then 2026 might bring more than meteors. What we should do first: demand transparency. NASA, ESA, and other space agencies owe the public complete data releases. If the Mars orbiters captured something anomalous, we deserve to see it. Second, keep watching. Amateur networks have already proven their worth. When institutions stay silent, independent observers fill the gap. Every telescope, every data point, every cross-referenced measurement matters. Third, prepare for the possibility that we're not alone, not in a panic, not in fear, but in rational acknowledgement. The universe is vast and old. The idea that we're the only intelligence is statistically absurd. If 3I Atlas is artificial, it's not an invasion, it's reconnaissance, a probe from another civilization, doing exactly what we'd do if we found an alien solar system: scan the planets, gather data, move on. But it does mean we need to ask harder questions and demand better answers. Conclusion: the question that won't go away. 2025, an interstellar visitor decelerated as it approached Mars. $4 billion spacecraft watched it happen. Contradictory data came back. Magnetic pulses were detected and then silence. No press conference, no papers, no answers. Why did 3I Atlas's trajectory against all statistical odds bring it so close to Mars? Why did it slow down? Why do our instruments disagree on what they saw? And why, when the scientific opportunity of a generation unfolds in plain view, do the institutions that spent billions to put cameras on Mars suddenly have nothing to say? Maybe they're being cautious, checking their data, avoiding premature conclusions, or maybe they know exactly what 3I Atlas is, and they're not ready to tell us. Subscribe to Narada of Shadows, because when Mars gets a visitor from another star, and the people with the telescopes go silent, someone needs to keep asking questions. The approach happened, the deceleration is real, the contradictions remain, and Mars might not have been the destination, it might have been the checkpoint. Next stop, Earth.